Let's consider OSPF neighbor formation in this video. First of all, consider this topology where we've got a couple of routers, and if they exchange hello messages, then they're neighbors. They reside on the same network link, so they've got interfaces on the same subnet, and they exchange hello messages. Well, that makes them neighbors. But they don't, just as neighbors, necessarily exchange LSA, link state advertisement information. Remember the metaphor we gave in our prior video about OSPF having a link state database, which is a map of the topology, and we compared it to building a puzzle, and we said those puzzle pieces that get exchanged to build the puzzle, to build the map, those are LSAs, link state advertisements. Neighbors don't necessarily exchange link state advertisement information. I compare it to a couple of neighbors that we have at our house. We have two neighbors that are even remotely close to us. Now, one neighbor we're very close to. We know the family really well. The lady that lives there is my wife's best friend. They talk and text all the time. We're very close. We exchange lots of information. The other neighbor that we have, I honestly don't really know them. I may have spoken to them once or twice. When they pass on the road, I throw up my hand to wave hello. I know what they drive, but that's really about it. We just say hello. We don't exchange any other information. And that's exactly what OSPF neighbors do. They just say hello. If we take it a step further, if we have a more in-depth relationship like we do with that one neighbor where the lady and my wife are best friends, that would be equivalent to an adjacency. An adjacency is when we have a couple of routers that are neighbors. We've got to be neighbors. We have exchanged hello messages, but we go beyond that. We exchange link state updates, which are the packets that contain link state advertisements. We have exchanged information to build this link state database. That's the distinction between being just a neighbor and being an adjacency, which kind of begs the question, why wouldn't we want everybody to be adjacent to one another on a network? It seems like it's better. We're exchanging more information. Well, the reason is scalability. Consider this. Here, I've only got 6 routers, but just to make the point, let's say that every router on screen, they all have an interface on the same subnet. If they were adjacent with one another, how many total adjacencies would have to be formed? Well, here's the formula. The number of adjacencies can be calculated with the formula of n times n minus 1. We take that quantity and we divide by 2. And in this case, n is the number of routers. So if we had 6 routers, n, 6, times n minus 1, 6 minus 1 is 5, so 6 times 5 is 30, divided by 2 is 15. It would take 15 adjacencies for everybody to be adjacent to everybody else. And that doesn't scale well at all. Consider 10 routers. If we had 10 routers, that would be 10 times 9 divided by 2. That would be 45. That would be 45 adjacencies. So what can we do instead? Well, what we can do is say that maybe 1 or 2 routers, they're high powered, they can handle some extra load. Let's have everybody form an adjacency with them, and then they can be responsible for propagating all this information out to everybody else. That way, everybody doesn't have to be adjacent with everybody else. We call those routers designated routers. Let's say that we're going to make R1 our designated router. And in case R1 were to go down, we'll have a backup. We'll say R2 is our BDR, our backup designated router. And with these designated routers, we only have to form adjacencies with the DR and the BDR. So now we dramatically reduce the number of adjacencies that have to be formed. You might wonder how we're communicating with just the DR or the BDR. It's using multicast. If we're using OSPF version 2, which is going to be routing for IP version 4, we're going to go to a multicast address of 224.0.0.5 to get to all OSPF speaking routers, or we could go to 224.0.0.6 to go to the designated routers, which includes both the DR and the BDR. If we were running OSPF version 3 and doing IP version 6, we would use the IP version 6 multicast addresses of FF02::5 for all OSPF routers and FF02::6 for the DR and the BDR. Now that begs the question, how does the DR get elected? Well, let's talk about the DR and the BDR election. This election is going to be based by default on the router priority. We can go in to OSPF router configuration mode and we can set the priority of that router. And we're communicating that inside of a hello packet with our neighbors. Now, sometimes we might not want that inside of a hello packet with our neighbors. Now, sometimes we might not want a router to participate in that election. Maybe it's a lower powered router. We don't want it to be accidentally elected as the DR or the BDR. So we can set a priority of 0. That's going to prevent a router from participating in the election. And whoever has the highest priority, they win. They're the DR. And the next highest priority is going to be the BDR, the backup designated router. But what if it's a tie? By default, everybody has a priority of a 1. What if we didn't bother to change that? How do we elect a DR and a BDR? Well, the tiebreaker is the highest router ID. OSPF keeps track of a router ID. We can see it in some of the show commands. And the router ID can be configured explicitly in OSPF router configuration mode by saying router-ID, and then we give a dotted decimal IP address, essentially. It looks like an IP version 4 address. We could say something like router-ID 1.1.1.1. Now, just because we say that, we're not advertising that network. We're just using that as our identification. If we haven't configured a router ID, though, it's going to be the highest IP address assigned to a loopback interface on a router. That's going to be our router ID. What if we don't have a loopback interface? Well, if we don't have a loopback interface, it's going to be the highest IP address on an interface that's currently up. That's going to win the election. And if you don't have that, you're going to get an error when you try to configure OSPF. It's going to say, yeah, you got to have an interface that's up in order for us to do this. So you'll not even be able to configure OSPF if you don't have at least one interface that's up. But that's a look at how OSPF speaking routers can form neighborships.